Hello student, I am Dr. S.L. Munde, Assistant Professor, Department of Mathematics, Sri RLT College of Science, Akola. Dear student, in a previous lecture we have completed unit number 5, that is game theory. So in this lecture we will start unit number 2, and that is integer programming. So in this lecture we will start introduction of the integer programming. So in introduction we will see the definition of the integer programming. What is mean by integer programming? The integer programming is also a linear programming problem. Okay. Then we will see the mixed integer programming problem. Okay. So before going to start, we will see the definition of the integer programming. Okay. So this integer programming problem is just like a linear programming problem. Okay. So in which all or some decision variables are constant to assume as non-negative integer values, and it is called as a integer programming problem. So in this integer programming problem, the decision variable or some of the or all the decision variable in a constant can be assumed as a non-negative integer values. Okay. So such types of problem is called as a integer programming problem. Okay. The mathematical form of the integer programming problem can be written as the objective function may be maximize or minimize. Okay, which is depends on the given problem. Okay, and it is written as, or it is given as c1 x1 plus c2 x2 plus and so on cn xn subject to constant ai1 x1 plus ai2 x2 plus and so on ain xn equal to br. Xj greater than equal to 0, where I equal to 1 to m, j equal to 1 to n, where xj are integer valued for j equal to 1 to n, and here p less than equal to n. Okay, so if you observe this term, so this term is just like a linear programming problem. This is the mathematical form of the linear programming problem. Okay, standard form of the linear programming problem. Okay, so we have already discussed in unit number 1 general mathematical form of the linear programming problem. Okay, so this integer programming problem is also like a linear programming problem. Okay, so this integer program is divided into two types. First is pure integer programming problem, and second is mixed integer programming problem. Okay, generally integer program divided into two types. First is pure and second is mixed. Okay, so what is the pure integer programming problem? We will see the definition first. An integer programming problem in which all variables are required to be integers. Okay, all variables are required to be integers, then it is called as a pure, or it is also called as a all integer programming problem or integer programming problem. For example, so let us consider the LPP, which is a minimize z equal to 9x1 plus 10x2 subject to constant 4x1 plus 3x2 greater than equal to 4, x1 less than equal to 8, x2 less than equal to 8, where x1 x2 greater than equal to 0 are integers. Okay, so this is the pure integer programming problem. Okay, so now we will define the mixed integer problem. Okay, an integer programming problem in which only some of the variables are required to be integers. Okay, here which all variables are required to be integers, then it is called a pure integer programming problem. Okay, and here in which only some of the variables are required to be integers is known as a mixed integer programming problem. Okay, so for example, maximize z equal to minus 3x1 plus x2 plus 3x3 subject to constant minus x1 plus 2x2 plus x3 less than equal to 4, 4x2 minus 3x3 less than equal to 2, x1 x2 greater x3 greater than equal to 0, and x1 as well as x3 are integers. Okay, so here the variables are, all variables are integers, and here some variables are the integers. Okay, now it is a mixed it is a mixed integer linear programming problem. So here you have to note that x2 is not required to be an integer. Okay, so here x2 is not an integer. Okay, so hence we can say that some of the variables are required to be integers. Okay, and here variables should be all the variable required to be integers. Okay, so this is the difference between pure integer programming problem and mixed integer programming problem. Okay, otherwise an integer programming problem in which all the variable must have integer value only 0 or unity is called as a 0 1 integer programming problem. Okay, must have all the variable must have integer values only 0 or unity. Okay, then it is called as a 0 1 integer programming problem. Okay, now we will see the some problems on a integer programming problem, pure integer programming problem, or it is called as a all integer programming problem. Okay, so there are some methods. So first method is a fractional cut method. Okay, first method is a fractional cut method, and which is given by the Gomori, and it is also called as a Gomori fractional cut method or cutting plane method. It is also called as a cutting plane method. Okay, an iterative procedure for the solution all integer programming problem by a Gomori fractional cut method or cutting plane method. Okay, and these are the some steps of the fractional cut method. Okay, so there may be the question in your examination: solve the given LP by using fractional cut method. What is the step number one? Step number one: express the given linear LPP into a standard form and determine the optimum solution by using the simplex method, ignoring the integer value restriction. Okay, when we will solve the problem, then we will see step by step problem. Second is test the integrity of the optimum solution. So there may be arises two cases. If the optimum solution admits all integer values, an optimum basic feasible solution is attained. Okay, if there will be the all integer values, then you will get the optimum solution. Second, if the optimum solution does not include all integer values, then move to the next steps. Okay, suppose there is a non-integer values, then we will move the third step. Step number 3: choose the largest fractional value of the basic variable and let it be the f10 k0. Okay, step number 4: express each of the negative fraction, if any, in the kth row of the optimum simplex table as the sum of negative integer and non-negative fraction. Okay, then we will express these non-negative integers, okay, into fractional part. Okay, then we will generate the Gomorian constant fractional cut, okay, in the form of, and which is given as g1 minus fk0 plus fk1 x1 plus fk2 x2 plus and so on fkn xn. So this is the first Gomorian constant, and where fkj lies between 0 to 1 and fk0 is 0 less than 1 less than 0 to 1. Step number 6: add a Gomorian constant generated in step number 5 at the bottom of the optimum simplex table, and then we will use the dual simplex method to find the optimum solution. Step number 7 is go to step number 2 and repeat the procedure until optimum basic feasible solution obtained. Okay, so these are the some steps of the fractional cut method, or you can see the cutting plane method, or a Gomori fractional cut method. Okay, now we will see the one example on a fractional cut method. What is the example? Find the optimum integer solution of the LPP by using fractional cut method. And problem is given as maximize z equal to x1 plus 4x2 subject to constraint 2x1 plus 4x2 less than equal to 7, 5x1 plus 3x2 less than equal to 15, x1 x2 greater than equal to 0, and are integers. Okay, so here x1 and x2 both are the integers. That means the pure integer programming problem, or we can say that all integer programming problems. Okay. Now, uh, now we will see the solution. Okay, step number 1, introducing slack variable s1 greater than equal to 0, s2 greater than equal to 0, and initial basic feasible solution s1 equal to 7 and s2 equal to 15. Okay, so we have already seen a simplex method. Okay, so by using simplex method, we can introduce s1 greater than equal to 0 and s2 greater than equal to 0 slack variable into the given constraint. Then we will obtain the initial basic feasible solution, that is s1 is 7 and you will get s2 equal to 15. Okay, then we will construct the objective function. Okay, so after that we will construct the first simplex table. Okay, then we will construct the second, third and fourth. Okay, so here the first simplex table will be cb 40 YB, Y2, Y4, XB, 7 by 4, 39 by 7. Okay, so these types of the simplex table you will get. Okay, so here you have to use the simplex method to obtain this table. Okay, now, now if you see, so here after using simplex method, you will get this simplex table. Okay, so if you observe here, all the zj minus cj value, or you can say del j values here are all are the positive. Okay, but here problem is not finished. Okay, so here up to these steps you have to solve the problem by using simplex method. Okay, but here if you see the here all the values of zj minus cj are the positive 1 0 1 0. These are the positive value, and this is the maximum value of z. But here the xb column here, x2 is a 7 by 4 and x4 is a 39 by 4. Okay, but this x2 column will not give the integer values, so these are the non-integer values. Okay, so since optimum solution is a non-integer value, okay, so therefore this table will not give the solution of optimum solution of the given integer programming problem. So here we will consider the fractional part of xb1. xb1, that is 7 by 4. So this can be written as xb1, and this can be written as 1 plus 3 by 4. Okay, 1 plus 3 by 4 we can write. So this is the fractional part and this is the uh, whole number part. Okay, xb2 39 by 4, so this can be written in this way. Okay, 9 plus 3 by 4, so this is the fractional part. Okay, so we can consider the fractional part of the both term. Then we will calculate the maximum f1 f2. Maximum is 3 by 4, here is 3 by 4, so out of them we can choose the arbitrary. So 3 by 4, that is f1 f2 both are the equal, so we can arbitrarily choose, select any one of these. Okay, so let us we consider f2, that is this f2. So in this second row y23, in this second row y23 minus 3 by 4, this minus 3 by 4 can be written in fractional part, that is minus 1 plus 1 by 4. Okay, and now we will add the Gomorian G1 into the in this table. Okay, by using slack variable. So G1 is minus F20, because this is the second row, F20 plus F21 x1 plus F22 x2 plus F23 x3 and so on. Okay, so using these values, that is minus 3 by 4 means this value, that is y, minus 3 by 4 means 3 by 4 fractional part. F21 means the fractional part of this term, Okay, f21, then f22 means 0, f22 means 0, then f23 means fractional part of this term, then f24 means uh, f24 means fractional part of this term, that is 0. Okay, so in this way we can construct the uh, Gomorian slack variable. Now we will add this Gomorian slack variable into this table. Okay, simply we will add here uh, in this row, below this row. So 0, G1, minus 3 by 4, minus 1 by 2, and so on. We will take the coefficient of this term. Okay, so this is minus 3 by 4. Okay, this is x1, that is minus 1 by 2, 0, minus 1 by 4, 0, and 1 by 4. Okay, so if you transfer this term to right hand side, okay, if you transfer this term to right hand side, you will get these steps. Okay, so after introducing Gomorian slack variable into this table and then calculating the Zg minus Cj, so you will get 1 0 1 0 0, and here you will get the, but here you will get the non-integer values. Okay, so again here we will get the non-integer values. So again we will use same steps, previous steps. So here xb3 is minus 3 by 4 is the negative. So therefore this variable leaves the basis. Okay. So since the maximum Zg minus Cj, so here we will use the which method, that is which method in we have given in this, that is um, dual simplex method. Okay, okay, so here we will use the dual simplex method to find out the income vector. Okay, so here minus 3 by 4 is a negative value, so using this, here is, this is the outgoing vector. By using the dual simplex method, income vector will be the x1. Okay, so x1 becomes basis variable in place of g1. Okay, so using income vector, outgoing vector, and this is the key element. Okay, so x1 will be the enter the basis. So after introducing slack variable, after introducing income vector and outgoing vector and key element, then you will get the this table. Okay, so again you will find out the Zj minus Cj here 0 0 1 by 2 0 2. Okay, but xb column will not give the integer values, so this will give the non-integer values. Okay, so here 9 by 2 and 3 by 2 both are the non-integer values. So again here uh, uh, we will introduce slack Gomorian slack variable. So here xb2 9 by 2, the fractional part is, that is 4 plus 1 by 2, 1 by 2 is fractional part, and 3 by 2, that is 1 plus 2, 1 by 2, that is also 1 by 2. So here 1 by 2 is a fractional part of this second row and third row. So maximum of this is f2 and f3. So here let us we choose arbitrary. So let us we choose f2 is 1 by 2. So therefore y23, in this y23 minus 5 by 2 minus 5 by 2. So that is can be written as minus 6 plus 1 by 2. Okay, the Gomorian constant can be written as minus f20. So this is the formula. Okay, this is the formula, and put here the fractional part of, that is f20 means that is minus 1 by 2, that is this minus and 1 by 2. x1 coefficient of x1, that is 0, then x2 means coefficient of 0, that is x3. X3 means the fractional part of this, that is 1 by 2, that is 1 by 2. Then x4 the coefficient of this fractional part, that is 0. Okay, so in this way we can construct the G2. Now transfer this term to left hand side, and here only remaining is that is minus 1 by 2. So this will becomes minus term. Okay, so adding in this row you will get the this table. Okay, so this table is same as this table, only you have to add this Gomurian constant. Okay, so again find out the del j minus then again find out the income vector, outgoing vector. Okay, so here Zj minus Cj is 0, 0, 1 by 2, 0, 2, 0. So again by using dual simplex method, here G2 is a outgoing vector, income vector will be y3, and k element should be that is minus 1 by 2. Okay. So by using dual simplex method, we can construct the final iteration, and which is given in this table. Okay, so if you observe all the values of Zj minus Cj, or we can say that del j, that is 0, 0, 0, 0 to 1, that is positive values. Here that means we can say that here all the values of Zj minus Cj is greater than or equal to 0, and all the values of xb and all the values of in xb column are the integer values. Okay, so therefore we can say that this table will give the optimum solution. Okay, and the maximum value of z will be the 5. Okay, so therefore this table will give the optimum solution of a given LPP. Okay, so here we will find out the x1. x1 means that is y1, 1, and x2 means that is y2, that is x2. So x1 is 1, x2 is 1, and the maximum value of z is that is 5. Okay, so put x1 and x2 in given equation, in given objective function, you will get the final answer, that is the 5. Okay, so this is the first example on all integer programming problem.